Welcome back. As I said earlier, the concept that we're going to learn right now, we will go into a lot more detail in the second semester chemistry course. But here I just want to simply introduce the concept and merely stick to the problem from a stoichiometric perspective. Okay. Now, this area of problem that we're dealing with is called titration, and this is actually one of the favorite labs that most of my students like when they do titrations, is because first, the lab is not very long and the calculation is straightforward. The chemistry is straightforward, so they always enjoy this lab. Okay, so you will see these labs next time you come back and take the class. But for now, we're going to just approach the problem and try to solve it. Now, there are some key words. Again, as I've told you when I taught you even the moles concept, there are certain ways a chemistry question has to be written. At least the math part and the units have to be written or coined in a certain way, right? If you notice, there's a key word here. It's called titrated. Means it's part of the general concept called titration. Most of you probably have done some type of titration if you've taken any chemistry class in your high school or anywhere else. Okay, so there's two things. One is called a titrant and the other is called a titrate. Okay, a titrate is typically what goes in, like say if this is your burette, okay, that contains some liquid, and then you have a conical flask that contains something else. So the titrate is typically what goes in a conical flask. It's usually large, small quantities of it. Don't take a lot of titrate. What you would put in the burette is your titrant. Okay, this is your titrant. This is your titrate. Okay. You don't need to memorize these terms because, again, this is nothing to do with you being able to solve the problem, but at least having a little bit of background knowledge about the problem you're going to solve is probably a good thing, right? So that's why I'm giving you this information. So titrated against means typically whatever comes after against. So this would be your titrant, and whatever typically for which you know your volume and concentration. Volume is indicated by mils, concentration is indicated by M. That's molarity. Again, we worked really hard to learn these concepts in the previous. So this is your titrate. Okay. You could solve this problem without knowing any of this information, but like I said, it's helpful to have a little background knowledge of the problem. Now, as with anything else, because we are still strictly approaching this problem not from any vantage perspective, but purely from a stoichiometric perspective, your first thing to do would be to see if the equation given is balanced. This is called a self-balanced equation. Means when you look at it, you do not have to balance anything. It's already balanced. Okay. So you can simply go ahead and put 1 for all of them because it's already balanced. You do not have to do anything. It's just 1, 1, 1, 1, 1. Okay. So here, if you notice, unlike the previous two problems where it's not asking for mass of a particular product. It's asking for something called equivalence point. Okay. That is, what is an equivalence point? Again, equivalence point, typically, at least it means that, okay, what is the equivalence point? Means when your moles of your acid, well, hydrochloric acid is your acid and is equal to moles of base, and which in this case is your sodium hydroxide. When this situation happens, that means typically you should have equivalence point, and this is what it's asking you to calculate. Okay, now if the acid and the base, this is the acid, this is the base. Okay, if I'm going to put this if in quotes, if acid okay, and base, okay, are in equal parts to start with, okay, then you could use your familiar equation that we learned on exam 1, which is, I'm going to write it actually in a different color, okay, V acid, we're going to convert the start and the end to acid and base, okay, so V acid times C acid, which is concentration of acid, equals V base times C base. You do not have to modify anything. Essentially, what it's asking for equivalence point means you're asking for what would be the volume it would take to get to that equivalence point, right? So we know volume of our acid is 250 mils. Concentration of acid is 0.5 molar. Volume of base is, so that's exactly what we're trying to find, and concentration of base is 0.2 molar. I'm going to put all those in brackets so that there's not too many numbers. Let's call it X, or you can just leave it with a question mark, and if you solve for it, and that's your answer. All I did is get rid of the start and the end from the previous and put acid and base instead. So because we are dealing with an acid and base. So this is mils, molar, molarity as well, so they cancel out. 250 250 times 0.5 over 0.2. It's 625 mils. That means this is the equivalence point where the moles of acid and the moles of base would be. I can mathematically prove to you how that is. Okay? So let's scroll down a little bit. This is just a proof, okay? This is just a proof or check point, if you will. The problem's already over. Like I said, if it's exactly 1-to-1, that's one part of acid to one part of base, then you can use this formula without making any change. The next problem we're going to look at in the next video, where we would have to add something to this B acid, C acid equal B base times C base to actually make the problem more useful. Okay, so the check point here is the equivalence point we said is moles of acid equals moles of base. Now this is exactly the concept we learned in our previous problem. Our acid, we're starting with 0.5 molar and 200 mils, right? How do you get moles? You answered this question on the exam. So 0.5 molar is moles over liter, 1 liter, and 200 mil is 0.2 liter. So that would be 0.5 times 0.2 is 0.1 moles, right? Let's do that same calculation for base. We're starting with 0.2 molar of base, so that's 0.2 moles over liter. And then we determined that this would have been 625 mils for base. This is for the sodium hydroxide, right? Because that's what the base is. So that would be 0.625 liters over 1. So it's 0.2 times 0.625. It's about 0.125 moles. Right? Now, if you see, oh, sorry, I made a mistake here. 0.25, right? It's 250 mils. I wonder why I was not getting the same number. So 0.5 times 0.25 is 0.125 moles. See? They're the same. So you don't have to do this. Again, all this is to add more value to your knowledge. Okay? The checkpoint is something you can do. You don't have to do. It's up to you. But the key here is if this number and this number is exactly 1-to-1, that's 1-to-1. That's what I mean by equal parts. then you could use this equation as it is without really making any changes to it. I'm going to box it. This is exactly the same formula that we used for our previous thing, but instead of start and end, we did change it to acid and base. Now, this is how you get an equivalence point. An equivalence point is nothing but the volume. So we did end up with volume as our answer. And the definition of equivalence point is moles of acid must be moles of equal moles of base. And we did prove that in fact they're all exactly the same. So we did do our math right. Very good. Now I'm going to stop here and then I'm going to come back with one more video for how when they are not exactly in equal proportion. All right? So stay tuned. Bye-bye.